Welcome back, everyone. We are here to learn how to draw a Lewis dot structure for a resonance structure. Okay, and I'm going to use carbonate ion as an example. Now, before we actually draw the Lewis dot structure of carbonate, we should have no idea whether it has a resonance structure or not. So let's assume that we don't know whether it has a resonance structure, and we'll walk through the steps as we go, and we will talk about the thinking as we draw the Lewis dot structure. So let me go very quickly to draw this structure. Okay. So if you look at the previous parts of the tutorial, you should know that we have the steps to draw Lewis dot structure. So the first step is to count the valence electrons. So we have 4 electrons from carbon and 6 electrons for each oxygen, and there are 3 oxygen total. So we have to times the 6 electrons by 3. Now, just like the previous example about the hydroxide ion, we have the charge, and we have to take care of the charge as we draw the Lewis dot structure. We have to take care of the charge when we do the valence electron count. So now the charge here is 2 minus. Okay, 2 minus. That means it has 2 more electrons than the protons. It gains the 2 electrons from outside sources, and therefore we have to include these 2 extra electrons in the Lewis dot structure. So we have to add 2 electrons at the end. All right? So keep in mind. Now let's work out the total. We have 18 electrons from the oxygen, okay? And if we add these all together, we have a total of 24 electrons, okay? Now I'm going to do the Lewis dot structure very quickly. Okay, so by this we draw 6 electrons from the single bond, so we have 18 electrons remaining, and then we're going to put the electrons onto the outside atom, since the carbon is the central atom. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So by distributing the electrons, the valence electrons on the outside atom, we have used up all the valence electrons available. Okay. Now the next step is we have to check. We have to check if every single atom in the Lewis dot structure, if they are octet. So the oxygen, they are octet because they have the 8 electrons for each oxygen. Okay. Now for carbon, if you look at carbon, it has 3 covalent bonds. There are 6 total of electrons. It needs 8. It needs 2 more. So now if you look at the examples that we talk about in carbon dioxide, we understand the fact that if the central atom needs more electrons, it will have to share the electrons with the outside atom. So here we are going to pick this oxygen, okay, to form a double bond. Okay? And to show that it is an ion, we have to put a bracket and make sure we put a charge as a superscript to make sure we tell people that this is an ion. Okay? Now you may ask, well, is that it? Well, if we draw the Lewis dot structure, yes, this is the Lewis dot structure for carbonate ion. But now here comes a question that you may ask. Why would you share the electrons from this particular oxygen but not these 2? Is it okay that we share electrons from this oxygen or this oxygen? Yeah, it's okay to share electrons from these 2, one of these 2 oxygen. Okay, I just randomly picked this oxygen to share the electrons. Now, the next question that you may come up with is that, well, are they actually equivalent to each other? Are they identical to each other? Well, let me draw them out. Okay. I'm going to draw a smaller version of the carbonate ion right here. Okay, showing that it's going to make a double bond right here. Okay, like this, or it could be like this. Okay, could be like this. So, so you may ask, well, if I'm working on a test, so which one should I put? Do we have to put all three, or do I put just one of them? Okay. Now the real question on this question is that are they identical to each other? If you look at these three structures, they look identical. Okay, it's very similar because it's just like rotating the ion around 120 degrees, and we get this structure, and then another 120 degrees, we get this structure. But what if we say that these three oxygens are not really the same oxygen? Now, you have learned what is an isotope in the past. And an isotope is when we have the atoms from the same element that are differed by the number of neutrons. So what if we say that this oxygen is actually oxygen 16? And this oxygen is actually oxygen 17. What if we say that this oxygen is oxygen 18? Now, then we have a problem, okay? Because we are actually bonding to make a double bond with these unique oxygen atoms, okay? And if we look at the other two structures, this would be the double bond between carbon and oxygen 17. This would be the structure between the carbon and oxygen 18. So these three structures are actually different, although they look so similar. So this is the reason why we have the term resonance, because they all look very similar, but technically speaking, they are not the same. So to include these other two structures, what we would do is to put all three structures together, and we will use a double-headed arrow between these structures to show that we have three possible structures for carbonate ion. Okay? Now, I want to clarify one thing with the double-headed arrow, because when we look at the double-headed arrow, it kind of gives people a sense of flip-flopping around, but that's not the case. What it means when we draw the double-headed arrows right here is to show that when we say about carbonate ion, we have three possible structures, okay, that could have different proportion in a sample. Now, in this case, we have no data. We are not going to look into the carbonate ion to see which is which, but we have to include these three possible structures, and this is what we mean by resonance structure. So in short, what we can say about resonance structure is that when we form a double bond or multiple bond in a molecule or a polyatomic ion, when you see there is a choice, okay, of where to make the double bond, it is actually telling you that we have different structures that could be very different, okay, although they look similar. And this would be a great example to show you what it is. Now, if you want to do a practice, I would give you a polyatomic ion that also shows resonance structure. It is the nitrate ion. The way you do the Lewis-Dot structure for nitrate ion is very similar to the carbonate ion. And what you will realize is that it will be very similar, that there are three possible oxygens that could form a double bond with the nitrogen. Okay, and this is the reason why we have a resonance structure for this polyatomic ion. So therefore, when we have this kind of scenario where we have options to make a double bond, we will include all the drawings on the paper, on the board, to acknowledge the fact that there are three or four, okay, or multiple possible structures that look very similar, but they are actually very different from each other. Okay, using the argument of they could be different isotopes. Okay, so in the next tutorial, we will do some more practice, and we will look at the structures, and we will look at how we actually draw the structures. Is there a particular way to arrange the atoms? And that will lead to the discussion of the shapes of the molecules. Now, you may have heard about the trigonoplanar, tetrahedral. Why do we have that? A lot of students think it's very difficult to understand that, but let me tell you this. That is the most interesting thing in chemistry, and when you learn the structure, you will understand a lot better on the physical properties of many matter. Okay, so thanks for watching this tutorial, and you can look at the next part of the tutorial on the Lewis-Stock structure and how it relates to the shape of a molecule, which means the Vesper model. Thank you.